Right now, as you watch this, your skin is running a program it has never stopped running, not consciously, not voluntarily, a deep physiological protocol that your body inherited from the humans who survived something most modern people will never face: sustained cold exposure with nothing between them and the ice. And here is the counterintuitive part. Your skin does not simply go cold when temperature drops. It runs a two-phase response, a controlled withdrawal followed by a deliberate rewarming pulse that has been precisely documented by physiologists and that operates the same way in your fingers today as it did in the hands of Homo erectus 1.8 million years ago. The question is, what exactly is that response? Where did it come from? And why does your body still refuse to let it go? Your body's relationship with cold begins at your skin surface. When temperature drops, the first thing your nervous system does is pull blood away from the periphery, away from your fingers, away from your toes, away from the skin on your face and ears. The mechanism is called cutaneous vasoconstriction, a narrowing of the blood vessels immediately under the skin, and it happens fast. Within seconds of cold contact, thermoreceptors in your skin signal the hypothalamus. The hypothalamus activates the sympathetic nervous system. Sympathetic noradrenergic nerve fibers release norepinephrine, and the muscular walls of the blood vessels in your skin contract. Blood retreats inward toward your organs and core. The exterior of your body becomes a barrier, an insulating shell. Research published in the journal Experimental Physiology confirms that this vasoconstrictor response is not limited to your hands. It is widespread throughout your body's peripheral shell during whole-body cold exposure. The result is a dramatic drop in skin blood flow that reduces the convective heat transfer between your warm core and your cold exterior. Research from the NCBI bookshelf Physiology archive documents that insulation begins to increase measurably when skin temperature drops below 35 degrees Celsius and reaches its maximum below 31 degrees. That behavior, the instinct to pull your limbs in, to make yourself smaller, to cross your arms against your chest, is the external expression of exactly this internal process. Your prehistoric ancestors did it, you do it. The physiology behind both is identical. But here is where your skin does something no one would predict. After 5 to 10 minutes of sustained cold, something unusual happens in your fingers, your toes, your ears, your nose. The vasoconstriction suddenly reverses. Blood floods back into the extremities. Skin temperature rises. Then, within minutes, the vasoconstriction returns. Then the dilation again. Then the constriction. An oscillating cycle, repeating rhythmically for as long as the cold exposure continues. This is the hunting reaction, first described by the cardiologist Sir Thomas Lewis in 1930 after he immersed a fingertip in 0-degree water. And the structure responsible for it is something most people have never heard of: arteriovenous anastomoses. AVAs are direct connections between arteries and veins in your skin. They bypass the capillary network entirely. In the skin of your palms, your fingertips, your soles, your nose and your ears, AVAs are densely packed, far more than in the skin on your back, your torso, or your thighs. When cold gets severe enough and the sympathetic hold on the AVA walls weakens or releases, these shunt vessels open. Warm arterial blood flows directly into the venous return of the extremity, bypassing the need to pass through the cold capillary bed. The finger reheats, the tissue stays viable. For the prehistoric human crossing frozen terrain, this response was the difference between functional hands and frostbitten, useless ones. Manual dexterity in cold conditions means grip. Grip means tool use, shelter building, and fire tending. Lose the dexterity, and you lose the survival chain. Research published in the European Journal of Applied Physiology documents that strong CIVD responses help maintain dexterity and tissue temperature of the fingers and toes during cold exposure and may delay the onset or prevent the occurrence of frostbite altogether. The protective function is not incidental to this mechanism. It is the mechanism's entire purpose. A 2026 meta-analysis published in the journal Temperature, reviewing the accumulated research across decades of CIVD studies, found the average onset time of the hunting reaction across all subjects was 7.9 minutes, with mean finger temperature at that point sitting around 10 degrees Celsius. The onset is not random. It is precisely triggered by a tissue temperature threshold at which frostbite injury begins to become a real risk. Think about what the prehistoric context demands of this. Groups of Homo erectus moving through glacial terrain in Europe or Central Asia, documented by the fossil record from as early as 1.8 million years ago. No insulated clothing, animal hides at best, cold water crossings, sustained contact with frozen ground and ice. Every member of the group needed their hands working, not warm, working. The hunting reaction, operating in their fingers precisely as it operates in yours, kept enough blood circulating at the extremities to maintain the mechanical function their survival depended on. The skin response alone does not explain how your ancestors survived sustained cold. Vasoconstriction and the hunting reaction manage the extremities. But to keep the core temperature stable across hours or days of cold exposure, your body runs a second system, one that burns energy specifically to produce heat without any muscular effort. Brown adipose tissue, or brown fat, is a metabolically distinct tissue found in the supraclavicular region of your neck, around your spine, and near your adrenal glands. Unlike white fat, which stores energy, brown fat burns it, directly and specifically to produce heat. The mechanism involves a protein called UCP1, an uncoupling protein embedded in the inner mitochondrial membrane of brown adipocytes, which diverts the normal energy production process and releases the energy as thermal output instead. Research published in the journal Physiological Anthropology in 2025, authored by Yonoshiro, Matsushita, Sakai, and Saito, confirms that in humans, prolonged cold exposure recruits brown adipose tissue, resulting in increased thermogenic capacity and improved cold tolerance. This recruitment happens within days of sustained cold exposure. The research further documents that cold acclimation via BAT is not just an individual adaptation. The data suggest it can be transmitted to the next generation through the paternal lineage. The activation pathway starts with cold. Your skin thermoreceptors signal the hypothalamus. The hypothalamus activates sympathetic nerves that innervate brown fat. Those nerves release norepinephrine. Norepinephrine binds to beta-3 adrenergic receptors on the brown adipocyte surface. This triggers lipid breakdown. The freed fatty acids drive mitochondrial respiration. UCP1 intercepts that process and releases the energy as heat. Your body warms from the inside without shivering, without burning glucose from voluntary muscle. The 2014 study published in the Journal of Clinical Endocrinology and Metabolism found that daily cold exposure not only increases the volume of metabolically active brown adipose tissue in adult humans, but also increases its oxidative capacity, meaning the more cold your ancestors experienced, the more efficiently their bodies generated heat without shivering. Your ancestors who survived long cold periods were not those who happened to generate more heat by shivering. Shivering is metabolically expensive and rapidly depletes glycogen reserves. The survivors were those whose brown fat could be recruited quickly, scaled up progressively, and operate across sustained cold without burning through the body's fuel supply. That capacity is still in you. Research suggests it is largely dormant in most people living in climate-controlled environments, but it has never gone away. The cold-adapted skin responses you carry, the hunting reaction, the vasoconstriction protocol, the brown fat system, are not uniform across all human populations. That variation is itself a piece of evidence. The 2026 temperature meta-analysis found that cold indigenous populations show shorter CIVD onset times than tropical populations. Research documented in a comparative study of tropical versus temperate populations confirms that cold-induced vasodilation strength and onset differ between groups with different historical cold exposures. Population studies cited in cold adaptation literature show that groups from sub-Saharan Africa, including the San of Southern Africa, display reduced cold-induced vasodilation in fingers and toes compared to populations with long histories in cold climates. Research published in Science, analyzed by Smithsonian Magazine in 2023, found that an extreme cold event, approximately 1.15 million years ago, may have driven early humans out of Europe entirely. creating a gap of around 200,000 years before a cold-adapted population returned. The humans who came back were described by researchers at University College London as having undergone evolutionary or behavioral changes that allowed survival in intensifying glacial conditions. The cold response systems in your skin are part of what that adaptation looks like at the cellular level. If you are watching this, you are descended from the groups that made it through. If you stay on this channel, what you will find is that every one of your body's responses to physical stress has a history this deep, and that history changes how you interpret what your biology is doing and why. The next video in this series covers something that happens in your body during illness that most people actively work against. Understanding why your body does it will make you reconsider every instinct you have when you get sick. Imagine you are standing at the edge of a frozen river, not the edge of a lake or a pool. A river. The ice is not uniform. It has fractured and refrozen in ridges. The cold is not an abstraction. It is a physical pressure on every exposed surface of your body. Your face, your hands, the skin of your forearms where the hide you are wearing has ridden up. You step onto the ice. Your feet are wrapped in hide, but the cold transfers through. Within seconds, your body has already begun its first response. Blood pulls back from your skin, not from your organs, not from your brain, from the periphery, your fingers, your ears, your nose, your feet. The surface of your body becomes cold. That is the point. The cold surface loses less heat to the environment than a warm one would. You are not alone. There are 4 of you making this crossing. The group moves slowly. This is not caution, it is efficiency. Slow movement on ice conserves heat, minimizes the metabolic cost of cold exposure, and reduces the risk of fracture. Your body is simultaneously running multiple systems: the peripheral vasoconstriction, the shivering inhibition that lets the muscles stay ready for action, and somewhere in the fat deposits around your neck and spine, the first activation of brown adipose tissue producing thermal output without any muscular work. At around the 8-minute mark of sustained hand-cold contact, something happens that you would notice if you were paying attention to it. The pain in your fingers, which has been building since the crossing began, briefly eases. The temperature of your fingertips rises a few degrees. The tissue that was threatening to go numb regains just enough circulation to stay functional. This is the hunting reaction. Your AVAs have released. Warm arterial blood is shunting directly into the venous return of your finger pads, bypassing the ice-cold capillary surface. Your body is not allowing your extremities to go dark. It is giving them periodic pulses of viability, not warmth, viability. The distinction matters. Warmth would cost too much heat. Viability is enough to grip, climb, and act. The crossing takes 20 minutes. You reach the far bank. Your core temperature has not dropped below functional range. Your hands are cold, stiff, and slightly slower than they would be in warmth. But they are working. The group is intact. The brown fat around your neck has been generating heat for the last hour. The vasoconstriction has maintained your thermal gradient across the entire crossing. The hunting reaction has kept enough circulation running in your fingers to prevent tissue damage. None of this was a conscious decision. The hunting reaction was not something your ancestor chose to activate. The brown fat was not deliberately switched on. The hypothalamic thermostat was not manually adjusted. Every element of this cold survival cascade runs automatically below the level of awareness, coordinated by systems that were calibrated by hundreds of thousands of years of crossings exactly like this one. Later, at the fire, the vasoconstriction reverses fully. Blood returns to the periphery, the hands flush, the ears warm. The rewarming itself is a separate physiological event, coordinated by the same system that managed the cold. Your body knows when the threat is resolved. It knows when to release the hold. The entire sequence, vasoconstriction, hunting reaction, BAT thermogenesis, peripheral rewarming, is the same sequence your body runs when you step outside on a cold morning, pick up something from the freezer, or plunge your hand into ice water. The scale is different. The stimulus is different. The physiology is not. So what does this mean for you right now? The first practical point is one that almost no one considers. When your fingers go cold and then rewarm on their own during sustained cold exposure, that is not your body malfunctioning. That is the hunting reaction doing exactly what it evolved to do. Research confirms this is a protective response against tissue damage. The appropriate response to that oscillating sensation is not alarm or retreat, it is patience. The biology is working. The second point concerns brown fat. Research from Frontiers in Endocrinology documents that exposure to mild cold, within the temperature range commonly found in climate-controlled buildings, is sufficient to generate a significant increase in non-shivering thermogenesis driven by BAT activation. You do not need glacier-level cold. 15 to 17 degrees Celsius sustained recruits the system. The problem is that most people in modern environments never encounter even that. The brown fat sits dormant. The thermogenic machinery your ancestors depended on waits for a signal that the thermostat permanently prevents from arriving. This is not a prescription. The research does not support telling you what to do, but it is important to note, as educational context, that the physiology of cold adaptation is contingent on receiving the stimulus that drives it. Your skin response, your hunting reaction, your brown fat thermogenesis, these are not passive features. They are trainable systems that respond to use. The hunting reaction, for example, has a measurable onset time, around 7.9 minutes on average in the published research. It does not activate in the first 2 minutes of cold. Your body is running through the initial vasoconstriction phase before it deploys the protective dilation. If you remove the cold stimulus before 7.9 minutes, the hunting reaction never fires. The protective purpose of the response never executes. This has implications for how cold exposure is interpreted and timed, though anyone with specific cardiovascular or circulatory conditions should treat this information as educational only and discuss any deliberate cold exposure with a qualified clinician. There is also the population variation point. The research on CIVD strength across populations with different ancestral cold histories is not a curiosity. It is evidence of the evolutionary mechanism at work. The colder the historical environment your ancestors inhabited, the faster and stronger the CIVD response tends to be. The physiology carries the record of what they survived. The AVA distribution in your skin is not random. Research published in Temperature and reviewed in the arteriovenous anastomoses literature confirms that AVAs are found in the palms, fingertips, soles, nose, and ears. Not in the back of the hand, not the torso, not the abdomen. Exactly the regions that experienced cold ground contact, cold water handling, and thermal exposure during prehistoric survival activity. The AVA architecture is a map of what your ancestors touched and where the cold hit hardest. The same structures that kept a prehistoric hand functional at below zero temperatures are in your hands right now. The hunting reaction that fired in your ancestors' fingers on a glacial river is triggered by the same thermal threshold in your fingertips when you reach into a refrigerator. The biological inheritance is exact, not approximate, not metaphorical. The mechanism, the threshold, the oscillating cycle, all of it transferred intact across 1.8 million years. The promise of this video was a specific one, the exact skin response your body inherited from prehistoric humans crossing ice. Not a general overview of cold physiology, not a metaphor, the exact documented mechanism. 3 systems, working in sequence. The peripheral vasoconstriction that creates an insulating shell around your core. The hunting reaction that pulses warm blood through arteriovenous anastomoses to keep your extremities viable. And the brown fat thermogenic system that burns lipid to produce heat without a single muscular contraction. All 3 of these systems are active in your body, inherited in exact form, running right now in response to cold stimuli that are a fraction of the intensity they evolved to handle. Your skin never fully freezes because 1,000 glacial crossings built a survival system that your biology refused to abandon. That person standing at the ice edge, running the same vasoconstriction cascade, the same hunting reaction, the same brown fat response that you run every winter morning, they did not think of it as biology. They just crossed. And their survival wrote the code that is in you now. The next video in this series examines something your body does during illness that feels completely wrong. and turns out to be one of the most precisely engineered immune strategies in your biology. Appetite suppression during infection is not a side effect. The research suggests it is a weapon, and understanding it changes every decision you make the next time you get sick. Your body is the accumulated record of what your ancestors survived. Every reflex, every threshold, every automatic response that fires without you asking. The cold response you carry in your skin is not primitive, it is precise. It was tested at temperatures that would kill you if the engineering had been 1 degree off. If your body's cold response runs the same program it ran 1.8 million years ago, then the question worth asking is, what else is running exactly the same program? What other systems in your biology are waiting for a stimulus they have not received in years? That question is what this channel exists to answer. As always, this content is educational in nature and is not medical advice. If you have specific cardiovascular, circulatory, or cold sensitivity conditions, speak to a qualified clinician before applying any information here.